So again, reminding ourselves that we have done carbon cycle in some detail in the first part of this course. I'm just adding a few more points from Andy Dessler's book. I also have a complete course on global carbon cycle if you are more interested in deeper aspects of the carbon cycle at all timescales, past, present, and future. So here we'll just touch upon a few points we have looked at from a slightly different perspective, which is always useful. So this is a schematic of exchange between the atmosphere, land biosphere, and ocean. Reservoirs are in gigaton carbon. Again, remember always there is a conversion factors between carbon and CO2, carbon dioxide. Fluxes are in gigaton carbon per year. So this is from this paper here. So atmosphere, this keeps changing every year. It's growing. So this is at 850. So you can think of almost this being almost double the concentration in ppm. It just works out that way. So this is at about 425 ppm here approximately, or a little bit less. So the exchanges between the atmosphere and land biosphere, which has a pool of 2500 gigaton carbon, is about 120 gigaton carbon per year in and out. So the net uptake for the land then becomes the difference of such large numbers as we mentioned before. So the vegetation is sequestering carbon but also respiring, and then there are additional contributions from deforestation, urbanization, and agriculture, other land use practices, which we generally refer to as AFOLU, agriculture, forestry, and other land uses. But keep in mind that we are looking for small differences between two large numbers, so the tracking of carbon cycle is always tricky. And land component, of course, also has the permanently frozen soil, permafrost, which has an estimated 1700 gigaton carbon stored in it. With global warming, it's thawing, and it has the potential to have a runaway melt or thaw of the permafrost by releasing large amounts of methane and carbon and increasing the warming. But so far the situation is still quite complicated, because thawing permafrost produces a lake sometimes, and the lake begins to have an ecosystem, but the lake obviously has different albedo than the permafrost with vegetation on top, and the ecosystem that begins to grow in the lake formed from the permafrost thawing complicates the carbon exchanges further. So the ocean mixed layer is the top turbulent layer, where the heating, cooling, rainfall, evaporation, and wind mixing create a well mixed temperature and density layer, also salinity, but there are complications in the vertical structure. So there is photosynthesis and gas exchange within the mixed layer as well, which has 80 gigaton carbon in and 80 gigaton carbon out. This number is often quoted differently by other people as 90, so you have to be careful there. But these are again estimates of global means. Large variability in space, as you know, from upwelling regions and downwelling regions and so on. If you want to go back to your oceanography lectures from this course, the reservoir size in the mixed layer, which tends to be order 100 meters, can be much shallower, can be a little bit deeper depending on how cold the temperature is and so on, but it gets complicated. So that's about 900 gigaton carbon per year. The difference between land and ocean is that ocean has a very nice three-dimensional structure with circulation, life distributed down to several kilometers. So it has an exchange with the deep ocean as well of 100 gigaton carbon per year in and out, and the deep ocean is a large reservoir of 40,000 gigaton carbon per gigaton carbon. And if you remember your residence time calculations, you can divide the reservoir size by the flux and get the average residence time of carbon once it gets into this pool, which is always important because once you take it away into a long-term storage, it is out of circulation from the atmosphere and ocean and doesn't play an immediate role in global warming. That's important, right? So expanding that a little bit, schematic exchange between the atmosphere, land biosphere, and ocean reservoir and the rock reservoir. So now we are not saying anything about the time scales here, but you can think of these as annual, yearly time scales. Of course, there is daily timescale gas exchanges as well as daily timescale carbon fluxes from photosynthesis, respiration, land, soil respiration, and so on. But this obviously gets into geologic timescale. So now we are looking at 46,000 gigaton carbon here, adding up 850, 25, all these numbers together. I hope that's right. 40 should be, yes. So this is 25 plus 17 is yes, 1600. So altogether it should add up. Make sure. Okay, so we have those exchanges, and you have a tiny flux from geologic timescales of rocks weathering millions of gigatons stored in them as a reservoir. That's the largest reservoir, of course. And you have this tiny flux, CO2 dissolving in water in the atmosphere, carbonic acid slowly weathering the rocks, and many of the geoengineering ideas we mentioned, like accelerated weathering, basically come from imagining that we can grind up rocks and create much larger fluxes to pull away carbon, because this exchange is 0.1 on geologic time scale, but it can keep on being stored in the ocean as weathered material goes into the ocean and gets exported through the processes we talked about here in terms of mixed layer and deep ocean exchanges. Okay, so there are massively different reservoir sizes as well as massively different time scale of exchanges, and of course the flux differences are also large. This is 0.1 gigaton carbon per year, whereas this is 120, so they are a couple of orders of magnitude larger. To take a historic Earth history type of time scale, atmospheric carbon dioxide over the past 500 million years, these are estimates of course, which rely on various proxies and some models to balance long-term carbon in the atmosphere, in the ocean, in land, and so on. Carbon dioxide in ppm in the atmosphere, you went from over 5,000 down to less than 1,000, a few hundred, increased back to over a couple of thousand, and over the last 50 million years we are cooling and carbon has dropped, and the global warming and anthropogenic emissions are happening in this context, because you should always remember that when you go back to the time of dinosaurs, it was much warmer and the carbon dioxides in the atmosphere were much higher. So the diagram of the carbon cycle as perturbed by humans can be now put in this context. Gray arrows show net flows of carbon caused by human activities. Arrows B, C, and D represent deforestation, enhanced absorption by carbon by the land biosphere, and enhanced absorption of carbon by the ocean, respectively. So these are the reservoir sizes again, too big here, 46,000 gigatons. Fossil fuels are adding right now about 8 gigaton carbon per year, converting the geologic time-scale reservoirs of carbon instantaneously into atmospheric reservoir, which is then moved into land and ocean. So you have the human perturbations of increased outgassing and uptake, and the same ocean is mostly taking up, whereas land has got a change in deforestation and enhanced absorption. So enhanced absorption and deforestation contribution. This remains same for now, but as you change the global mean temperature and rainfall distribution, this can change on longer time scales because amount of CO2 in the air and the warmer temperatures accelerate weathering rates, which we have talked about elsewhere. Okay, so abundance of carbon dioxide in your atmosphere over the past 10,000 years, 250 years, and 50 years. So this is what we have been looking at mostly in terms of the Keeling curve. Okay, so the panel C shows a gray curve, the annual average carbon dioxide abundance if all of the carbon dioxide emitted by the human activities since 1959 had remained in the atmosphere. So we know how much we emitted, and we know the rest is going into land and ocean, for example, and the reservoir that the sinks that are into land and ocean, if they didn't do their job, then you would keep on accumulating in the atmosphere, which is increasing, and the difference between them is increasing as well. And of course the question is whether land and ocean will continue to take up carbon the way they have been, or whether they will get saturated and the accumulation in the atmosphere will accelerate. Okay, so that's the carbon dioxide over time. This is for 10,000 years. You can see the relative jump we have made in the anthropogenic timescale since industrial revolution. We came out of the last ice age at below 280, and before the industrial revolution we had raised it slightly up to about 280, but now we are accelerating the increase with about 4 ppm per year, which is going to increase. At the rate of increase is going to increase. Rate of increase is going to increase because of fossil fuel burning if we don't do anything about it. 750 years, this dramatic increase looks less dramatic since the industrial revolution, but we should keep this in mind because this is the period over which we evolved as modern human beings, and this is of course the increase in the Keeling measurements since the 1950s. We can always take the time derivative of this and show how the CO2 in the atmosphere increases over longer time scales and how it changes year to year. So the bars show the observed year-to-year increase in atmospheric carbon dioxide. The solid line shows what the annual increase would have been had 100% of the carbon dioxide emissions remained in the atmosphere. So here the interannual variability or the year-to-year variability here comes from what the El Nino is doing, what La Nina is doing, what forest fires are doing, what volcanoes are doing, what droughts are doing, and so on and so forth. Okay, so large dips are often related to the natural variability or impact of volcanoes and so on. Okay, so keep that in mind. Now again, looking at fraction of carbon dioxide remaining in the atmosphere after an initial pulse in year 0. So if we somehow pump suddenly some amount of carbon dioxide into the atmosphere, the time scales at which the ocean and land take up the carbon dioxide and how the atmosphere land ocean system equilibrates takes such a long time scale. So you can see the plot shows it takes very long time for carbon dioxide emitted to the atmosphere to be completely removed. Okay, so the scales are changing here. So this is the 100 years, and then the next 1,000 years, and the next 10,000 or next 10,000 years. So residence time of carbon dioxide in the atmosphere is very long. It's an inert gas, well mixed, and it stays around for centuries. So the idea is that essentially we are putting a pulse of carbon dioxide into the atmosphere relative to the time scale at which things change, which means even if we immediately stop putting out more carbon dioxide, it will take a long time, multiple centuries to multiple millennia, for it to be drawn down by the system. Similar things for methane. So methane has gone now. This is an order of magnitude, several orders of magnitude smaller. Methane is typically measured in parts per billion by volume, not parts per million like carbon dioxide, but here it's converted to parts per million. So over 10,000 years, we have again made a significant jump in methane emissions from coal burning, large-scale agriculture, dams, and wetland loss of wetlands and other things, cattle. And this is how it looks since the industrial revolution. Okay, so we have increased it more than double since the beginning of the industrial revolution.